Welcome to your first video lecture of Physics 107. Today we're going to talk about electric fields, and this is really kind of a continuation of a topic that you've already discussed a little bit, that is charges, Coulomb's law. All of that stuff is related to the new concept that I'm going to be talking about today, that of an electric field. So we're going to start in a place that should be familiar territory at this point. Let's say that I have a positive charge. Let's say that it has charge plus Q, so a positive charge. I'm going to call this my source charge. My source charge, for reasons I'll get to in just a minute. And let's say I've got another charge over here. Let's say it's also positively charged, and I'm going to give this a symbol Q0. And this is a charge I'm going to refer to as my test charge. Now, you guys know that if I have two positive charges, there's going to be an electric force, and for now I'm going to focus on the electric force that the test charge feels. And so this gets to why I'm referring to these things as source charge and test charge. You can think of the source charge as the thing that's doing the pushing or the pulling, and the test charge as being the thing that's feeling that push or pull. First of all, if they're both positive, we know that this guy is going to experience a force that is away, because it's a like charge, from the source charge in this case. And in particular, if this distance between the two charges, if I call that r, then I can compute exactly what that force is. And we know that this force is going to be in this direction. So the test charge is going to feel a force up and to the right. And we can write down the magnitude of that force from Coulomb's law. We know that the force felt by the test charge, the magnitude of that force, which is why I dropped the arrow sign here, I'm just talking about the magnitude for the moment, is going to be K Q0 over R squared. Now I'm going to define a new concept at this point. I'm going to define something called the electric field at this point right here. So I'm going to define it to be the electric force felt by the test charge divided by the magnitude of the test charge. Okay, that's my definition for electric field. Right away you can get a sense of the units, of what the units are going to be for this thing. The units are going to be, in SI units, force is in newtons, charge is in coulombs, so an electric field has units newtons per coulomb. Now in this context, so this is a general definition, but in this context that I've drawn right here, the electric field magnitude is just going to be this stuff divided by Q0, which means the Q0 is going to cancel, and I'm going to be left with K Q over R squared. So this would be the electric field set up at this point by my source charge. Okay? Now, what does this physically mean? Well, an electric field is something like a hypothetical force. Specifically, if I erase my test charge at this point, and instead of actually thinking of a real test charge being at that point, let me just call this an arbitrary point in space. I'll call it P1. You'll notice that my electric field definition does not have Q0 in it. It doesn't depend on the test charge. I've divided the test charge out, effectively. Which means that at this point, I've defined a quantity known as the electric field vector, even though there's no charge there to experience it. If I pick a new point over here, the electric field is going to be defined at that point. Call this E1. And in this case, R is smaller because I'm closer to the charge, and so E is going to be bigger. So this would be my electric field E2. I can pick an additional point over here, call it P3. Electric field now has a value at all points in space, right? Even though there's only one charge, the source charge. Okay? So what do I mean about this hypothetical force? Well, it means that if I take a test charge out of my pocket, a Q0, and I place it at P1, then I immediately know that it's going to feel an electric force, Fe, that's equal to Q0 times E. It's going to feel a force in the same direction as E, and its magnitude is going to be Q0 times E. So in order for there to be a force, I have to put a charge at P1 there to feel it. But regardless of whether there's a charge there or not, there's still an electric field. So that's what I mean by hypothetical force. So this is kind of a new concept, this idea of a field. Probably not one that you've experienced before. But it's going to turn out to be very useful for a number of reasons. What if I have more than one source charge? No problem. If I say have one charge here, call it Q1, and let's say it's positive. Let's say I have another charge here, Q2, and let's say it's negative. And I'm interested in a point over here. See, this is my point of interest. I can ask, what is the electric field set up by these 2-point charges at point P? Q1 is positive, and so Q1 by itself is going to set up an electric field at point P that points in this direction, because electric fields point away from positive charges. So I'm going to label this as E1. Charge 2 is negatively charged, which means if I were to put a positive test charge at point P, it would feel a force, an attractive force, towards Q2. And so, by definition then, my electric field, due to this second point charge, is going to point towards Q2. So to find the net electric field at point P, I have to consider the vector sum of E1 and E2, which is going to graphically kind of look like this. So I'm setting up a little parallelogram, and so my total electric field vector at point P is going to be the vector sum of these two guys. So there is my total electric field vector. It's going to point up and to the right a little bit. Now, again, there's no charge at point P. There's nothing there. I've set up an electric field even though there's nothing physically at that point, right? In order for a force to exist, I would have to put a charge there to feel it, right? So again, an electric field is a hypothetical force. Note that the vector EP, that actually has nothing to do with the force that Q1 exerts on Q2 or Q2 exerts on Q1. I'm imagining that these two source charges are fixed in space and that they're creating an electric field at all other points in space. It's an important distinction. Yes, there will be a force exerted on Q2 by Q1, but that has nothing to do with the electric field that these two charges by themselves set up, okay? As you can probably imagine, the electric field is kind of a complicated thing. It's defined at every single point in space. And how do you keep track of something like that? That's kind of a difficult thing to do. I mean, I could, for example, pick a bunch of points and draw little arrows at all of those points with the right lengths, and I would have kind of a feel of what the electric field looks like at all points in space. But that gets time-consuming and tedious. And so it turns out there's another way to visualize electric fields that's a little more organized, and that is to draw electric field lines. And I have some rules for drawing electric field lines and how and what they mean, but I'm going to do an example first, and then we can go over the rules. So I'm going to imagine that I have a charge here. Let's say that it has +3 units of charge. So in some units, I'll say it's +3Q. And let's say that I have another charge over here that is -Q. Try to draw that again. -Q. Okay? This collection of charges is going to set up an electric field at all different points in space, and we would like a convenient way to visualize that. First thing we're going to do is we're going to draw hairs on these charges. Okay? And the number of hairs we draw on each charge is going to be proportional to the magnitude of the charge. So in this case, I'm going to try to draw about 3 times as many hairs on the 3Q as I'm drawing on the -Q. So let me start by sketching, say, 5 hairs on the -Q. So 1, 2, 3, 4, 5. I'm going to kind of try to do it in an even distribution like that. which means I need to draw 15 charges on the 3Q. Now that's a little bit hard to do, so I'm just going to draw 16 and call that close enough. It's not bad. And an easy way to do that is to draw one at 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock, and then 3 in between each of those markers. So 1, 2, 3, so I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Right, so this has 16, this has 5. That's a close enough ratio to actually get a reasonable picture here. Then the game is just to connect as many of the lines as you possibly can. This one clearly can go straight to this one, right? Now, since electric fields like to point away from positive charges and towards negative charges, I'm going to put a little arrow on this guy going this way. And so then maybe this one I'm going to connect with that. And so in order to do that, I'm going to have to sort of warp my line a little bit to do something like this. Same thing with the one below it. And I'm going to put arrows on all of these. The next one comes from here, but that's got to wrap all the way around to this hair over here. And so that's going to, again, that's going to kind of be warped like that. Now I'm in a situation where I've run out of hairs on the minus Q side. And so what am I going to do? Well, the only option at this point is to draw electric field lines that go all the way to infinity. And so I'm going to kind of try to continue this warping pattern like this and then complete my picture. This one I'm just going to draw straight to the left by symmetry, and then I've got something that looks kind of like that. So here is my picture of electric field lines. You'll notice that if you kind of think of an analogy with airflow, it's as if the plus 3Q is like a hair dryer, and this is something like a vacuum cleaner where the lines leave the plus 3Q and get sucked in by the minus Q. But of course, there's more stuff coming from the 3Q than there is going into the minus 3Q. What's the advantage of this picture? Well, it means that I can pick any arbitrary point, say one right here, and the electric field vector at this point in question is going to be tangent to the field line, right? So the electric field at this point would look like this. The electric field right here, for example, would look like that, right? Even though there's no field line actually drawn at a point right here, there still is an electric field. It's not as if the electric field at this point is 0. So the electric field still exists at this point in between the field lines, even though I haven't actually drawn a line there. In reality, there's an infinite number of field lines. We sort of just sprinkle to get a feel. You see where the field lines are really tightly packed together, like right here close to the plus 3Q and in between. The field must be very strong. Where the field lines are really spread out, such as somewhere over here, the field is going to be very weak. So this is one of the general properties of electric field lines. And so with that in mind, let me list a couple of general rules and properties for drawing field lines. Number 1, field lines always start at positive charges or at infinity. Number 2, field lines always end at negative charges or out at infinity. Both of those cases you can see very clearly here. Again, the number of lines either leaving or entering a charge is proportional to the charge magnitude. Number 4, the denser the field lines, the stronger the electric field in that region. Number 5, electric field lines can never cross. It's not possible for one electric field line to poke through another field line. If you had something like that, then you would have a weird ambiguity where does the electric field point this way or does the electric field point this way? Right? At some point in space, there would be ambiguity there. So field lines can never cross. It's not possible. And finally, and this will be something that is of some importance to us a bit later when we talk a little bit more about conductors. It turns out that lines contact conducting surfaces always at right angles. So if you imagine that these are conducting spheres, I've kind of drawn them as if they're actually real solid objects, you'll notice that the field lines are always emerging from these objects at right angles. And that's going to always be true for conductors. Okay? That's a useful thing to remember for a little bit later. Okay, that's all for now. I have a couple of follow-up questions for you to think about conceptually, and I'll see you next time.